so they execute. Okay, so again, we need a def with 3 sides, one side for the RTL, one side for the data pad, and one for the control pad. And I will have to simulate that def by flashing papers back and forth. Okay, so the first thing we want to do is we want to take register 29 and subtract. So let's say we have register 29 here. We want to subtract or add. Let's say we have it as A. So, okay, but to say that it's you're right, add. So to say that we have it in register A, that means if it's 25 through 21 have to have 29. So let's write that in. If it's 25 through 21 have to have 29, 16, 8, 12, 13. So that's 29. Okay, we'll finish that later. So we have 29. We want 4 coming in here. We want, eventually, before we decide where to allocate the 4 field, eventually we want to, for popping, we want to take something from memory and stick it in $reg. That's what the pop instruction is going to do. It's going to take out, it's going to read something from memory and stick it in $reg. Maybe I'll write that because people are looking at me stunned. Destination register of pop value. Okay. So we want to be writing this register. How can we write the register? The write register is bits, either bits 20 through 16 or bits 15 through 11. Let's use bits 20 through 16 because maybe we'll use the immediate or something. Maybe not, but we don't know yet. So let's use bits 20 through 16 for the write register. Everybody see why I said that? Don't copy this down blindly. What's important is what I'm saying, not copy this down. That's kind of obvious. Okay, so we're getting somewhere. Now we need a 4 coming in. To add 4 to this, well, the immediate field is not used, so we might as well bring in 4 in the immediate field. So let's bring in 4 in the immediate field. Okay, so we got the machine code done. Hopefully we didn't screw up too bad. Okay, so what happened at the end of decode? At the end of decode, we had register 29 and A. So we have 29 and A, so that means we can get the 4 coming in here, so we can add the register 29 and 4 and stick it in ALU out. Okay? So cycle 1 of execute, ALU out gets A, register 29, plus 4. So that is, leave a couple of lines here. Cycle 2, you have to write that into the register file. So, RF of bits 20 through 16 of the instruction register get what's in ALU out, and that data pad already exists. So, RF of bits 20 to 16 of the instruction register gets ALU out. Again, I told you to leave a couple of lines there. So that gets the PC, I'm sorry, not the PC. That gets the register 29, gets register 29 plus 4 part. We haven't done the part where we're reading memory and I screwed up. Did somebody see how I screwed up? I really screwed up. paying attention to my English. I said register 29 gets register 29 plus 4. This is not register 29. This is register red. So what we want to do is get bits 25 through 21. You should have caught me there. If that was a really bad screw up. Okay, so that gets the stack pointer gets the stack pointer 1 plus 4. Maybe I will put a comment here. $SP gets $SP plus 4. That's basically what it's doing. That's not part of the RTL. That's just my comment to explain it. Okay, that's one part of it. Another part of it is you want to read.
Professor,
Yes.
don't bits 25 to 21 go to read register? On the second cycle,
Yeah, we're gonna have to change the data path. I was gonna do that later, but yeah, I'll do that later. Well, since you asked, I'll do that right now. Okay. No, I'll do that later. Okay. Okay. So we want to read memory. Where are we reading memory from? We want to read what is in the old value of register 29 or the address in the new value of register 29 for a pop. Old, right. So the old value of 29 is in A. So that is the address that we want to get into the. Oops, what did I do? I pressed something. I think I'm okay. That is the address that we want. Unfortunately, the address is coming to the ALU out, and that's not going to quite work. So what I want to do is I want to get register 29 into ALU out. Okay.
Do another cycle then?
Yeah, we need another cycle. Well, we definitely need another cycle, but the question is, where should that other cycle go? We have registered 29 in ALU out here. I'm sorry, in A here. So we want to get it into A again here. So I will write this. This is strictly speaking not needed, but in this course I'm going to require it. A gets RF of IR of bits 25 to 21. Okay, I'm getting register 29 into A again, and the next cycle I can get register 29 plus a 0. So that means I'll need to add a 0 here into this box. So the next cycle I'll get ALU out gets A plus 0. Okay, so now so where am I? So I have registered. The push the stack pointer change has been in process, but I have the address that I want to write in ALU out. I have the data that I want to write. I'm sorry. I want to read that. So that's going to come into here, and I can read that into the NDR. So in this cycle, I can get the NDR gets mem of ALU out. Oh, but that's not this cycle. That's cycle 3, because ALU out just got done in cycle 2. Okay. So now I've read the value that is being popped. What do I want to do with it? I want to take MDR here, and I want to stick it into the register file.
Yeah.
And since register bits 20 to 16, I can do that. Actually, you know what? I'm gonna start again, because I did a bad design. My design. Well, I'll do this, and then I'll make it better. The next cycle, I'll get RF of IR of bits data path changes that are needed here. One data path change is something that somebody already pointed out. That was, what did they point out? Registered file of IR 25 to 21. So 25 to 21 does not happen, does not go to here. So that is one data path change. And another data path change is that the registered file of bit 20 to 60. No, another data path change is the ALU out gets A plus 0. A plus 0 is not a possibility in this architecture. However, now this one we can now say is easy enough to fix. If you notice, we never even used this immediate field because this 4 is already supported in this data path. So we didn't really use the immediate field. Everybody see that? We didn't use the immediate field, so why are we storing 4 in this immediate field? Instead, we could avoid this other data path change, the 0, by sticking a 0 in the immediate field. So let's do that. Let's change this. Let's change this from a 1 to a, let's make this a 0, and instead of a plus 0, we will use A plus the immediate field sign extended. Because the immediate field comes here, you sign extended, it's still a 0, and you get 0. So instead of a 0, you get IR, well, sign extend of IR that's 15 to 0. So we made our design a little better. Just because I initially thought about using an immediate field for 4, and I didn't really need to, so why bother? Okay, so now we've made a better design. Still 6 cycles because fetch equal plus 4 execute cycles. But but we still need this one data path change. So let's make that data path change. Okay, so let's use Brown. The data path change is I want bits 25 through 21 coming into the ALU, coming into the register file. So the register coming into the register file write register because that's the register being written. So bits 25 through 21, I'll use a finer point. I think it's finer. So bits 25 through 21. I want to bring that down into here. And let's call that input 2. Now, in general, for the multi-cycle, we want to minimize data path changes. We want to make the changes in the control, not in the data, unless it's absolutely needed. In this case, it's absolutely needed. But in general, we will not be making data path changes in the multi-cycle. Okay? Okay, so that's the data path change we need for this one. Now we can mark up our control path. ALU out gets A plus 4. Well, first of all, where is it branching from? I guess I will use this shade of blue. If off equals pop, kind of rhymes, we want ALU out to be A plus 4. How do we make ALU out to be A plus 4? We want to get this much to be A and to be a 1. ALU stores A to be a 1. ALU stores B to be a 1, or a 4, and ALU to be an off. circle around it after I decide that that's all I need. So that is for this ALU out. This one comes for free because that's the only thing that A can do. So that is our state here. Okay, so that is step cycle 1 of our RTL. Cycle 2 of our RTL. RF of IR 2521. That means this must. Well, first of all, everywhere where we see a reg desk, we have to change it to 2 bits. So let's do that. So reg desk, any reg desks here. So this 1 becomes a 0, 1. This 0 becomes a 0, 0. Did I miss any reg desks? No, I did not. Correct me if I didn't. But now we want this reg desk to be a 2, because we're doing this thing. ALU out is going to be, this mux is going to be a 0, which is called a mem to reg. So mem to reg is a 0. Reg desk should be a 1, 0. Okay, so that, and we also want to do a reg write. And again, remember, if, for read write signals, if we don't mention it, it means it's a 0. For control signal, other control signals, we don't mention it, it means don't care. So reg write is called reg write, okay? So that takes care of the first line of this RTL. The second line of the RTL, ALU out, gets A plus the sign extension. How do we do that? A coming in here, so that means ALU source A is a 1. The sign extent of the immediate is here, which is 2, and it's an add. So ALU source A equals a 1. ALU off is an add. And that takes care of this one. And that's all we had for as far as cycle 2. Okay. Cycle 3, MDR gets a mem of ALU out. Let's see how that happens. MDR is here. Yeah, that gets written for free. You don't need any control for that. You want to do a mem read because you're reading the memory. You want the address to be ALU out, which is input 1. So this mux, which is called IRD, you want IRD to be a 1, and you want mem read to be a 1. IRD equals 1. So that was cycle 3 of this RTL.
HDR, ZAMA.
So we just have one more cycle to go.
With the Z.
So everybody good so far? Yes.
One question, why did you choose all the red stuff to do this?
Because I needed, because of the data pad change that I made, where is it? Here. Because this became a 3-to-1 mux. So I have to change the existing ones.
Was there an ALU source A? Was that ALU source B?
Pardon me?
Under ALU source A on the second part.
Oh, the second part. You put a living point here.
No.
Here.
Yes.
Okay. So what's your question?
I can't see what it says.
Oh, ALU source A is 1 and ALU source B is 1, 0. cycle you said? You mean this one? Yes, I read right. Well, you remember, for read-write controls, if we say it, it means it's a 1. If we don't say it, it means it's a 0. Because otherwise, every stage is going to become like huge, by convention. Okay, so we have cycle 3 done. Cycle 4, let's see what we're going to do for cycle 4. Register file of IR of 620 to 21. So that means this flux, which is regdef, has to be a 0. Regdef has to be a 0. This flux has to be coming from MPR. So this flux, whatever it's called, mem to reg is a 1. So regdef is a 0. Mem to reg is 1. And we're doing a write reg. Okay. So regdef equals, what do they say, equals 0. We are doing a reg write. I'll write this up here. And we are doing, the mem to reg has to be a 1. And I think that's pretty much it. I guess I'm calling it a reg write. Are you done? Any errors? Any questions? There is an error.
Don't you have to loop back?
Yeah, exactly. So we have to loop back otherwise we just made a cycle. We made a CPU, which the pop instruction is the last instruction that ever be executed because it's a dead end. So we loop back to the fetch. So we added an instruction. And again, I will repeat what I said multiple times. In general, we want to minimize data pad changes. Most times you will not have any data pad changes. Because we will be making the changes in the control pad, not in the data pad. Because for a multi-cycle, we really want to, we're pretty much done with the data pad. We just want to, in this case it was unavoidable because we needed an extra pad. But in general, we're pretty much done. We don't want to make changes here. Don't mess with this. Yes?
In the cycle bubbles, does it matter what order it goes by?
What do you mean?
So like which order you write it in? So say you swapped IRD with
Yeah, we could have written the RTL. That's a good question. Yeah, again, there are multiple answers. We could have written the RTL to do the other part first, and then the SP gets SP plus 4 part. We could have done that. I don't know. Try it out. Maybe you'll even save a cycle. I don't know. Maybe you'll lose a cycle. Maybe you'll save a cycle. I can't answer without trying it out. And but the one thing you do not want to do is you don't want to do this to completion and then the other part to completion. Because pop is doing 2 individual things. You want to kind of merge them together because it's obviously going to be inefficient if you do one part of it first and then the other part of it, right? So in this case, cycle 2 was the one where we merged both parts of the instruction together. Different stages in both parts of the instruction together. I'll repeat it because people are kind of looking confused. You don't want to do, a pop involves 2 things. It involves changing the stack pointer, it involves reading something from memory into a register. You don't want to say, I'm going to do one of them for completion first, and then I'll start thinking about the other one. I mean, maybe you'll do that when you're designing it, but eventually you want to end up combining them to save a cycle. And we did that here because cycle 2 actually had a little of quota in there. Okay. You had to put your hand up.
Oh, yeah. In cycle 1, why did we put register J9 back in A? Is it not already in A?
Yeah, but it gets written every single time, every single cycle. However, in this particular architecture, it doesn't really matter because the only thing that gets written into it is that there's no choice. So in this of convention, I'm gonna write it, I'm gonna expect you to write it every time. And I'll also remember a rule that you're not allowed to write RTL, which at one line, which does not, in which the right-hand side registers do not appear as the destination register on the previous cycle. So here, we're using A on the right side, so it must appear on the left side of the previous one. It appears by, yes, it appears by default anyway, because there's no choice in this particular implementation, but that's an implementation issue. Okay?
Could you show the data packages?
Yes.
The changes on the code.
Yeah, the changes are here, yeah.
I mean, like, when you marked up, like, the station.
Really?
Oh, that's me, the control pad.
Oh, yeah,
Really?
sorry.
Why?
The first addition, the one label on
See
the
what it is?
top,
Yeah.
that one is for adding 4 to A, right?
It's for the first line of RTL. Remember the RTL that we had under here? It's the whatever corresponds to the first line of that RTL. Which happens to be A+4, yes, but that's not the point.
Why is ALU source key equal
0, 1.
0, 1? Oh.
Sorry. Oh yeah, the 1, 0, 1, the 1 got cut off a little. Now it looks even more of a 0, 0. Okay, this is 0, 1. Hey, everybody, I'm gonna yell really loud. This is 0, 1. Okay. Yes.
In general, when we're writing a new instruction, how do we determine when like one cycle ends and the next one begins?
I'm not sure what you mean. The question was how do we determine when one cycle ends and the next one begins? I mean, if in every line of RTL, you have to make sure that the right-hand side of that RTL is assigned to by the previous cycle. And if it's not, then you did something wrong. Okay. So any more questions on POP? This implementation of POP. Again, there is multiple ways of doing it. Well, one of you suggested a way of doing the, instead of doing the SP+4 part first, do the memory part first. Try it out, maybe it'll work better, maybe it'll work worse, I don't know. This is just the way I did right now. I mean, I didn't prepare anything, I just did it from scratch. But the important part of the design is not this, it's not this, it's not this, it's not this. The important part is the RTL. Once you get the RTL, this is kind of stupid. I mean, this is like completely trivial. It just follows from the RTL. It's just bookkeeping, clerical work. And this normally will be very trivial. In this case, it's one minor change. So the important part, for single cycle, the important part was the English. For multi-cycle, the important part is the RTL. So don't even bother. Sometimes I see people like, oh, I'll do the RTL last because you want me to submit it. But they tell me how to do this. No, I'm not, I'm gonna refuse. You have to do the RTL, and I'm gonna tell the tutor to refuse. You have to do the RTL first. It does not make sense to say, I'll do that last because you want me to submit it. Okay, the RTL that goes first, and then everything else is pretty much bookkeeping and clerical stuff. Why is everybody like rubbing their shoulder and their foreheads? Multiple people are.
We're all bloggers.
Not that's for that statement, but in general. So write the RTL. Once you write the RTL, everything is free. Okay, so then so no questions on that. So let's talk about how we. This is 160 review, but a couple of people asked after class last time. And I was going to do it anyway. There's this big block called control. How is this represented by that control block? This is a state machine. In 160, you learn how to implement state machines as logic. And I also alluded to it in the slides that we did at the beginning based on Appendix some appendix. But let's do a very, but even though even though it's review, let's do a simple example of a state machine, of designing a state machine. Okay. Yes.
Before we get to that, I'm just going to ask, were you planning on like showing us the data path for the top?
I think I did.
The diagram.
I did.
The diagram itself.
Which diagram?
The data path.
I mean, didn't I do that? I think you're asking something different than what you said you did. But this is the data path.
So all that. So if you were to give us this on the exam, all you want us to do is the data path change that you put on.
Well, the data path change is trivial, yes.
I think she's asking like, can you, like, you know how previously when you open the data pack, you would like draw little parts of parts.
Oh, yeah, that would, well, even then you're not required to actually trace things out. You could do it if it helps you learn. But here, I mean, I guess you could trace out the paths, but I'm not sure that's really going to be very useful.
And what would you?
The RTL is what is useful here.
I just like I feel like seeing the data path.
Okay, well, let's do it, but I don't think it's going to end up being that useful because it's enforced a different cycle, so we have 4 different colors, so we're just going to end up with a mess. Well, let's do it, then you see that it's a mess. Okay. So let's bring up the RTL. So in cycle 1, so let's say blue cycle 1, ALU out gets A plus 4. So that's that. On cycle 2, I guess I will do green. Register file of bit 25 through 21. Oh, sorry, I screwed up.
Check your LinkedIn, bro. Check your LinkedIn, bro. Gets ALUL. Okay. And ALUL gets A plus this sign extent field. Cycle 3, what other colors do I have? Orange. Cycle 3 is going to be orange. MDR gets mem of ALUL. ALUL. Yeah, I guess that's it. Oh, the right data too. No, I'm sorry, hold on. Mem of ALUL. No, that's a read, that's not a write, never mind. Okay, so that's that. And then cycle 4, I guess I'll use yellow. RF of IR 20 to 16. That's the MDR. So that's this one. MDR goes here. So that's how we would trace it out. Again, I'm not sure that this is really going to help you a whole lot. Again, RTL.
Thank you so much for doing this.
Yeah.
I think to like reword my question a minute ago.
Okay.
I guess looking at step 3 and 4 on
because in Ford, you need MDR. MDR is not available yet. It's only written in cycle 3. So you could not do these two together.
So it's whenever we write a state element, it's when we basically have to start a new cycle.
Yeah. Now you can write multiple state elements, and right here you're writing both RF and ALU. But if you're using one of them, then you have to start a new step cycle. Again, it's entirely possible that there's some other design that is able to compress this into 3. I'm not guaranteeing that this is the best implementation. But it probably is, but I'm not guaranteeing it is. But it's definitely not the worst. I will guarantee that. Okay, back to how to implement a state machine. So we have a state machine like this. So let's make a very simple one that we're going to implement. Let's have a 3-state machine. And another state machine also has conditions in the arcs. So let's have one case, let's have a condition. Let's say x is an input. X equals 1, and x equals 0. That's like our op, in our state machine we had, sometimes we had a branch depending on what office. Here we're going to have a branch depending on what x is. The other ones don't have a branch. And let's say, in our state machine, we had about 15 or so outputs. I don't know how to count it. But let's have just one with just one output. So let's say the output is y equals 1, y equals 0, y equals 1. This is some random machine. I'm not. Okay, so how do we design this? We also need to number our states. So let's say this is state 0, 0, this is state 0, 1, and this is state 1, 1 for whatever reason. If you remember from 160, actually figuring out what is the 0, 0, 1, 0, 1, 1, 1 assignment, that itself is a problem that you analyzed in 160. We're not going to do that. But let's assume that you did, based on your 160 knowledge, you did that. So now we have to design the circuit. How do we design the circuit? We make tables. We make a next state function and an output function. So our next state function, the next state is based on the input x and the current state. So x, current state 1, current state bit 0, next state bit 1, next state bit 0. So the current state is 0, 0, 0, 1, I'm sorry, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1. Okay, if the current state is 0, 0, the next state is 0, 1. If current state is 0, 1, then it depends on x. Then the next state would be 0, 0 if x is 1, 1 if x is 1. If x is 0, it is 0, 0 if x is 1. If the current state is 1, 0, the next, well, it's a don't care because we don't have a current state of 1, 0. The current state is 1, 1, and the next state is 0, 0. That's the next state function. The output function. Output here, in 160, you may or may not have talked about mini machines and Ford machines. It really doesn't matter, because it's either equivalent. If the current state is 0, 0, current state 1, current state 0, y. If it's 0, 0, then you have a 1. If it's 0, 1, then you have a 0. If it's 1, 0, 1, 1, 1, 0 is a don't care, and 1, 1 is be a 1. now you have a table. They have two tables. Stick this in a Karnaugh map. And you can come up with some circuit for the next state as a function of the current. You have the current state, well, actually just the state. You have a function of the next state is a function of x and the current state. So this is the next state function. So the current state goes into there. X goes into there. And then the next rising edge, you change to the next state. You know how to make Karnaugh maps for this. Output. Another Karnaugh map. Based on the current state, you have some output. What is the output? The output's Y. We're done. Use 160 techniques, whether it's Karnaugh maps or Klein-McCluskey or something more advanced. Well, I mean, all the CAD tools, they use something which is based on Klein-McCluskey, possibly with some heuristics. And you use those techniques to come up with what goes in here, what goes in here, a bunch of games. This circuit goes in here. This control block is basically that circuit. And that's all there is to it. Any questions? This is a completely 160 review. This is nothing new. Don't look so stunned. Okay, so we're going to go on. Okay, so we're finished with the multi-cycle. So let's evaluate what we have. Again, I will repeat this so many times, but I will repeat it again. Single cycle, the whole point was that you make a clock cycle long enough for the longest instruction. And it's going to be fairly long. So you have a slow clock rate, but every instruction takes one cycle. Multi-cycle, maybe not an example we're going to do, but in general, you have a fast clock rate, but the slowest instruction will be longer because it will take so many cycles. But hopefully the fast hopefully 90% of the instructions will be faster. And if 90% of the instructions are faster, then on average you will be faster. So let's make some timing now. How do we figure out the clock rate for the multi-cycle? I guess I need to pull up another diagram of the multi-cycle, which I will do. Where did all my figures go? Here. Okay. Okay, so we're going to again we're going to assume some times, and let's say all our muxes are 2 nanoseconds. Let's say ALU. Anybody remember how fast our ALU was before? I'll just make something up. Nobody remembers. Okay, so I'll say 10. It doesn't have to compare to what we had before. Let's say our memory reads are 20. Let's say our memory writes are 20. Let's say our memory reads are 16, and our memory writes are 20. Let's say a register read, the memory read is 16, let's say the register read is 12, and the register write is 14, let's say. And control. Let's say our control is going to be, actually, let me tell you something which I wasn't going to, but since it fills in nice right here, maybe we can make this one work off the
let's make, let's make the controls free. Okay, so now we want to figure out the time. How do we figure out the clock rate for this multi-cycle processor? Well, what happens in one clock cycle? What happens in one clock cycle is one state. So we have to take the time for this, the time for this, the time for every single one of them, and take the largest one. Okay. So the time for cycle 2 is 0. So I'm going to zoom out. So if you haven't written down the big stuff, do it now. So cycle 0. What is cycle 0? It is doing they're doing a mem read, and it's doing an IR. So it's getting the instruction, and it's also getting PC ALU source of 0, 0. So that's going to be PC. So it's also doing the PC plus 4. Okay, so let's figure out how long that's going to take. It's going to be the larger of reading this into the instruction register. So this is stable at 0. This is stable at 2. This is stable at 18. And I'm saying the instruction register writes are free. So it's the larger of 18 on the PC plus 4 business. So this is stable at 0. This is stable at 2. The other input is also stable at 2, the 4. This is stable because control is free. This is stable at 0. So largest input is stable at 2 plus 10, which is this is stable at 12. This is stable at 14. So at 14, you can write the PC. Okay. Cycle 1, you're doing that's basically doing the branch address computation, adding source 0 and source 1, 1. Yes. Hold on. Let me just finish this one and then I'll get to your question. So you're adding this 3, 2, and 1, 1. That is input 2, which is free. So this is 2, 2, 2, 0 plus 10 is 12. So cycle 1 is going to be 12 nanoseconds. Now the question.
What are you taking the max?
Can we quiet down, please?
What are the two values you're taking the max of?
One was for the PC plus 4 path, and one was for the instruction fetch path part of it. What's going into the IR. Okay, let's not do every single one of these because we can kind of eyeball it and see that some of these are just not going to take that long. Let's do some of the memory ones. Let's do cycle 4. Cycle 4, what is it doing? It is, no, I'm sorry, that's not, no, let's do cycle 3. Cycle 3, what is it doing? It's doing a mem read based on IRD equals 1. So if IRD equals 1, that IRD is coming in here, so it's doing it's picking that, so the address is stable in 2. You're not using the write data for reads. This is stable in 0. So at 18, this is stable. So in 18 seconds, you get something into MDR. So cycle 3 is going to be 18. You can already see that this 20 is going to be more than that. So let's do the 21. Which state is the one that's writing memory? That is, we're not doing the pop. So the one that's writing memory is cycle 5. What are we doing in cycle 5? We're writing memory based on IRD equals 1. So this is stable, IRD coming in here. This is stable at 2. This is stable, that's free. So this is stable at 0, 2. This is free, plus 20. So that's 22. And at this point, I am just going to assert that everything else is less than 22. IRD equals 1. IRD equals 1 means this is stable at 2. This is stable at 0 because it's coming from a register. So 2 plus 20 is 22. Okay, everything else, others, less than 22. I'm just going to play God and say it is less than 22. Okay? So what does this mean? This means the clock rate, the clock cycle time is at least 22 nanoseconds. Greater than or equal to 22 nanoseconds. Let's say it's equals. So that means the clock rate, let's see, 22 into 1,000 would be 880, 990. That would be approximately 45.5 megahertz. Somebody can, if somebody has a calculator, please confirm. Anybody? Okay, it doesn't matter. Okay, let's just say this. Okay, so the clock rate is 46 megahertz on this design with these numbers. I don't remember what we had earlier in single cycle. It really doesn't matter. But now we want clock rate is not important. What we want is the MIPS rating. So let's compute the MIPS rating. For the MIPS rating, we need to have we need to know how many. We need to know the instruction mix. So let's assume, based on extensive simulation and extensive analysis of benchmarks, so we'll assume archive, load word, store word, let's see, how many paths do we have? We have branch, we have jump. So as a rough rule of thumb, branches are approximately 1/7 of the instructions. So let's say this is 5% and this is 10%. Because 1/7 is getter is 14. Let's on a load store architecture, we're not going to be doing that many loads and writes and stores. We are going to be the whole point of a load store architecture is that we're doing lots of stuff in hard type. So let's say the store word. I don't want to use the 5 again, so I'll use 4. And let's say a load word is I don't want to use 10 again, so I'll use 8. So what does it add up to? 10, 15, 27. So we need let's make this 12. 12, 16, 31. So let's make this 6. 18, 33. So that makes this 67. That's somewhat reasonable. Somewhat realistic. Okay, so let's say that is the instruction mix. So what is the MIPS rating? The MIPS rating is going to be 67% times R type. We're going to be a little late today. 4 cycles. So CPI equals 0.67 times 4 plus 0.12 times the load word takes 1, 2, 3, 4, 5 cycles. Plus 0.06 times 4 cycles. Plus 0.1 times 3 cycles. Plus 0.05 times 3. Which happens to be 0.68, 328, 352, 382, 3.97 cycles, if I did my arithmetic right. So that means the MIPS rating is going to be, we know how many instructions per second, how many cycles per instruction, and we know how many cycles per second. So we can compute the instructions per second. So that's going to be let's finish this next time. Okay. I can say it.